Thank you for coming. I know that we are after lunch, so you need to find the food coma. So bear with me. We're going to go this together. I'm going to talk about a few things that we have done at Netflix creating large data sets. And I will try to expose a recipe of the things that we use and employ, and maybe you can benefit from some of it. This is me. My name is Pablo Delgado. I am a machine learning engineer at Netflix, and together with me is Jack Ye from LanceDB. We are co-presenting because we're using the product they offer. The research team that this work is entitled to, it's Mahdi Kalayev, Austin Slakey, and Ashish Rastogi. They are part of the content, media, and foundations at the moment of this talk. So let's talk a little bit about data curation. So if you've seen literature on these new models that accept multimodal, you might see that the input on some models, generative models, is text and images. Contrastive models also text and image. And for video diffusion models, you have video and text. So it will look like very easy now just to get a bunch of videos and a bunch of text and pass it through these models and train. And that's it. You get the model that you want. But apparently that's not the case. You need to curate and select precisely the data that you're going to use in order to train those models. If you explore different papers, this is the paper of MovieGen presented by Meta like 2 years ago, I think. And they showcase this curation pipeline where you have the raw data represented in the large pool of videos. And then you process them by filtering quality, filtering content length, filtering motion. You also need to filter by aesthetics. So if the video is pleasant aesthetic to the eyes. Then you need to also caption to provide a text description of what the video is doing. And all of this is represented as a pipeline, but it's a very complex mechanism that you need to do stage by stage until you find the actual valuable data that you need to use to train. Another paper, this is Goku, another video generative model. You can see represented in green the raw assets that you can have, a bunch of images, bunch of videos. And there's a process where you transform the data into that data that it can be consumed, like videos turn into frames or turn into crops of a video. And you can also, in yellow, see all the stages that you use to filter, because you don't get metadata for free. You need to produce the metadata for the videos or for the images. So you need to score them, you need to classify them, you need to do a lot of machine learning on the data in order to be able to filter it. And later on, you have captioning and the scoring of motion, or if you want to create different data sets to train. And lastly, you also need to balance the data sets. Some data sets are heavily headed towards a type of content, and you want to balance it so the model understands diversity much better. This is another picture from a model called One from Alibaba. This is a report from last year. This showcases the flow of data. In pink, you have the total pool of all the data that you can gather. And then you start having stages where you filter the data. You need to annotate the data, filter, and go to the next stage. Annotate the data, filter it one more time. So the gray areas are the data that you discard and you don't need for the next stage. And then you create a different points in time. You create pre-training data sets, which might be lower resolution or more large in content. Then you can filter to produce more high quality for another stage of training, which might be medium training. And finally, you can get the very, very best and use that to have a data set for self-supervised fine-tune or supervised fine-tune. So the curation recipe might entitle these 3 pillars that I want to mention. One is you need to be able to have a diversity of models that you can use throughout your journey on the data. If you are curating audios, you need a bunch of models that can understand audio, classify audio, curate audio. If you are managing videos, you need to have models that understand video, can curate video, and those things. You also fine-tune sometimes these models to produce the desired output. So you need to have a way, an API storage system, all to manage the models, so you don't have complications when you start doing this pipeline. Another thing that you need is batch inference. So these models are very expensive, and they expensive to use. You need to use GPUs sometimes, most of the time. And you need to do a batch inference to do all of the data, to scale all the data that you need to process. And finally, you need a storage system to preserve the data and filter the data and query the data. At the same time, you go back to square one where you do more inference. And finally, you need a lot of GPUs to get away with this. So let's dive a little bit into one of the pillars, which is models. Models, what is the role in data curation? So we cannot curate the images by themselves if we don't have a model that tells you what the image is about. Or if you in this case, we have an aesthetic score that will assess if the aesthetic is high or if the aesthetic is low. So you can filter out the low aesthetics. Another model that you can use is a visual language model. You can query and interrogate the images or the videos and tell them, describe what you see in the video, describe the motion, describe the lighting. And you can capture text that describes your primitive data. Not everything is models, of course, but for audios, you have audio in, a spectrogram out. So that's you can consider it as a model. It's a transformation. And you can also turn an audio into a text. And all of this becomes the data that you need to use in order to filter and manipulate these models. For embeddings, you use models like Clip or Dino. So you have a representation, a vector representation of what the image is about. The same way you can treat text and have a vector representation of what the piece of text is about. Then you can operate on the vectors instead of operating on the images. There are models that require more than one input. So in this case, Clip's core, you get the vector representation of the image, the vector representation of the text, and you compare the two vectors and see how similar they are or how dissimilar they are. What about videos? How do you do this with videos? So if you want to get an embedding of a video or a clip, not actually a video, but a clip of a video, you extract images, and for every image you do a clip embedding, and then you get a vector embedding, and then you collect an average or a mean embedding of all the frames. So that will give you, if you think of it geometrically, you can see you project the images on a space, and you have the geometric center of where they land. And then now you have a vector that represents your short clip, and then you can use it to compare against other vectors, other elements inside the data set. Likewise, if you want to caption, if you want to add text to a description of a video, it doesn't work directly on a video, but you use a model that is fine-tuned, an instruction model that is fine-tuned to understand that the frames that you supply are part of a video. So in some models, you annotate frame 1, frame 7, frame 20, and you need to annotate the number of the frame, and the model understands that. In some other models, you just put the array of all the images, and then you supply all the questions that you want in order to annotate the videos. There are other models that the input becomes the output, so you can have an input image becomes a depth image. You can do this for video too. If you do some models preserve the temporal aspect of this, so you can do one image at a time. You enter with an image, frame 1, and you output the depth of frame 1, and you do this over and over for all the frames. You get the video, a video in, a video goes out. One very particular API that is very easy to use, the ergonomics at least, is high phase. We use it extensively to fetch models and manipulate models on this curation. You can use the pipeline API. The pipeline API is very simple. You define the input. You initialize the pipeline with a string, and the string here is the name of the model. In this case, is depth, anything. And then you produce, with the input image, you produce the output depth. And this is very simple, and it lets you chain a lot of models together with this pipeline API. If you are more venturous, you can use the auto classes, and with that you can independently have a piece of the model that it will pre-process the data input, the model itself, and then in an inference loop you can predict the output of the image, and then after you have the image, you have a tensor or something that it's not very compatible with the input, you can transform that and format it in a way that you can also understand the output. How does it look like? All of these things, models, conversions between one thing or the other, is so you can filter a corpus. So here we have the top aesthetic scores, very clean image, very sharp. You have a character in the center. Sometimes you have photographic composition as well. The very bad are blurry, or the camera was pointing to the floor, or By the way, all of these are not random images. They are images taken from movies. So you have frames. So sometimes the frames look at a different direction, or you have the motion into account. So you need to discard the rubbish. The ones in the middle are interesting because you don't know if they are very good or very bad or whatnot. So you need to go into a second stage to purge or curate with more discerning capabilities what's in the middle. Another thing that you might think of when you do these curations is that you do derive assets. So every time you start with an image, you derive it into a caption. Here we have a short caption. Also, you can ask a detailed caption, and the detailed caption can describe every aspect of the image. We also have metadata that comes with where is the image taken from this movie, from this year, from this genre. So we can annotate the talent, in this case, Jennifer Lopez, instead of a woman. And we can also capture the show and who is present, at what time, and what scene. So it's very, very useful to aggregate and keep adding to the pool of data that started initially with just images. We have shot classifiers, so you can say, given an image, I can pass it through a classifier, and the classifier will tell me if it's a close-up, a extreme close-up, a full shot, or wide shot. These are all cinematographic terms, and you can classify them and balance your data set if you want to train with enough close-ups and enough wide shots. Also, you can plot the embeddings. So the embeddings are very useful for deduplication. So you can find when communities are close together, they might be identical. So you might be having the chance to deduplicate a lot of the data. You can also balance data sets. In our case, we have a lot of human faces in our photographs. Photographs is frames. So you might want to balance out the number of faces and get more dogs or get more cars, which is something that you need to do in order to train. And it favors exploration. You can explore the communities. You can explore, for example, here we're rendering a cluster of women with guns, which is something naturally occurring in an embedding space. Okay, so we went through models. Now we have models, and we know that if we pass the model to some of the multimodal data, we can get some data that we can then filter by or group by or do things. But how we operate on these models? So we need to talk about batch inference. So this is the way pictorially you accommodate. You start with the white columns, which are the columns that you start with, and via a model, you create another column with scores. Via a model, you create another column that is the text description. And you keep adding models and chaining models, and every model becomes a column in your data. So you can, for every time you pick an entity, you have all of these aggregated derived assets that you can use for. So in order to pass a model through the data, you need to have an inference system. One of them is the online inference aspect. Online inference, you have a model in one machine, and you have the client in another machine. So you have a thread that reads the data, one payload at a time. You submit it to a server. You wait for the response. this is all in slow motion, by the way, but now it's all instant. So you get the payload back, and then another thread saves it to the disk. So this is normally the case when you have a closed source model, or you have a different language in the server than in the client. Say you have a server that is in C++, and your client is JavaScript, or I don't know, Python. So then the mismatch is overcome by having an HTTP or gRPC request. If you have to coordinate many models, as we've seen, we have many models to do pass over the data, you need to have a very robust client that can go to one model, come back with a payload, and with that payload send it to the second model and that payload. So you will see that all the yellow payloads are intermediate payloads. That the output of one model, you pass it to the next model. So the client here has to be a multiple coordinator that understands failure tolerance, understands how to retrieve and retry things. It becomes very, very complicated very quickly. But this is the solution that people do when the models are outside or around. So companies, external companies that host the models and so on. Another idea of this is the bulk inference. Based on bulk synchronous parallel, you might think of it as you have a machine that has the model, and that machine is the one reading the data. So you read the data, you process the data with the GPU, you save it back in the same thread. If you do multimodal, you need to read the data, process the data, save it to an intermediate, and then read the intermediate, pass it to the second model, save the intermediate, and so on. And this will generate as many copies of the data until you finally have the last version of the dataset. In this picture, the models might be hosted in many machines. So every stage that says model 1, model 2 might be many machines, many instances of the same model. So you need to wait. The bulk synchronous parallel here signals that you need to wait until the stage in yellow finishes before you can engage into the next stage, and then you can engage to the next stage. And this is very common in frameworks like MapReduce and Spark, where you do this synchronous. Ray data, Ray is a framework that came from one of the Berkeley labs, comes with an elegant solution about this, which is called, I call it Ray batch inference, which uses shared memory. Shared memory is a memory that you share among many machines. So here you have a thread that reads a portion of the data into memory, and that memory location is shared via pointer. So you can deploy machines with models, and the machines exchange pointers from memory. You don't have to copy the data from one place to another. The data lives in a memory location, so you can just exchange the outputs and inputs via pointers. And finally, another thread at the end picks the resulting batch and save it to disk. So this is, if you squint, you can think of it as a streaming system. You are collecting the data from the input, you are processing the data, and you are saving it back at the same time. In another picture, you can imagine, you can do heterogeneous CPU, GPU computation of your data. In this case, the two stages in the middle are elastic as well. So you can see CPU stages where you fetch and resize the data. The stage in the middle has 4 instances of a segmentation model, and the next stage has 3 instances. So you can elastically allocate how many instances you need in order to preserve the throughput throughout the pipeline. And then another CPU task will write the results to this, remote storage, or a database, whenever you want. And the API is also very simple. If you map your thinking into the API of Ray, you will have a way to describe the processing or the model. In this case, it's just a callable. You can call the model with a batch, and you output the model output directly. You can do read the data, process the data, mapping over elements, and saving the data. So read, process, save. And if you notice, the concurrency here is 2,10. That's elastic, meaning you start with 2, and if you need more, you can grow up to 10, and when you don't need it anymore, you can collect it back to 2. So this elasticity will allows you to have every stage accommodate for the throughput coming from the previous stage. If you pile more stages, you can say, read the data, map over dyno, map over aesthetic, map over quality, map over gemma, and then save. And you need to allocate differently. Gemma is very heavy, so you need more instances to process data. Dyno is super lightweight, so you can accommodate less instances. So this you can do by yourself, or you can let the system accommodate. A high-level overview might look like this. The pipeline in a high level looks like the blue path. So you go blue, 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 resize, filter, captioning, assessing, do clip embedding, and finally saving the pre-computation. Or you can think of it that filtering is not only one stage. You filter by non-safe for work, then you filter by aesthetic, then you filter by Villa score. And all of these stages, you can interchange models to assess which model is better for the task that you need. Okay, so we went through what you need to process data, which is models. How do you process the data with the batch inference? And now we need to think about how we can store this data. This data is very massive, very large. So one way to think about this is parquets are immutable. So we started this journey reading and writing parquet files. And if you add or append rows to a parquet file, in reality what you're doing is you are copying the previous data and you are appending the new data. So every time you need to carry on the previous data set with you. So growing the data, it's painful sometimes. Another way of thinking of this is if we are growing columns on the data, it might be good to keep around the deltas. And the deltas can be, if I have a terabyte data set and I add a column that it's 1 terabyte, I might add the delta of 1 terabyte instead of 11. And so on, every time I add a new column that represents a large amount of data, I carry around the deltas instead of copying the data set over and over again. And we play with different schemas, different solutions, and we came to this product called LanceDB. And they came with the realization that data sets grow at the same time adding columns that you are adding rows. So new data comes in, it adds, appends as row. New features or new research ideas comes in, you need to add columns. And this two-dimensional growth of the data makes it very painful with the existing system. They came up with the idea of having a columnar format that supports zero copying, so you don't need to carry your previous data set, you keep growing the data set. A manifest that points to the changes on the data set, and they provide also implicit vector search. So you can vector search your way into embeddings without ingesting this data into another system and having pointers with two systems. So pictorially it looks like this. You have a manifest, and think of it as a commit operation. So if you have a file that represents the column 1 in version 1 and you append some rows, you add another file that represents the green, the extra rows, and you append that into a manifest and say, now your data set or your table is constituted of version 1 and version 2. These two are your entire thing. If I later on add a column, which is the most interesting case, another file represents the column and you have a manifest that points to the new column. So now your data set is portion 1, portion 2, and portion 3. And you keep adding portions in 2 dimensions and you can grow your data. Another way to think about this is internally it works. You have, let's say you have already a data set with columns 1, 2, and 3, and they are represented with logical partitions called fragments. And if you decide to add columns 4 and 5, you loop through every fragment, and for every fragment you append a file that describes the new 2 columns and the new 2 columns in the second fragment. And then later on you add rows, you append another fragment, and you put the files of all the columns. So in the end, these different files constitute the 2-dimensional data set that you have. Programmatically, if you do this with an array, appending a column in green, it's a program that does some operation with the input and produce an output, and you run it with add columns. You just open the file, add columns, and output the file. Jack will talk a little bit more in detail about this. Then you have the query access patterns. Now you have the data and you want to become one with the data, you want to explore the data, you want to filter, you need to query the data in the same place where the data is. You don't, if you need to query embeddings by copying all the data to an embedding database, you query the embedding database and then you need to come back with the IDs to query the data itself. Lance provide these indexing mechanisms. So you can use some columns for doing regular SQL with filters and the algebra for SQL. You can have full text search, so you can do decompose your text into elements that can be queried by just a string. And then you can use vectors and use vector search for finding nearest neighbors embedding in an embedding column. And if you want to train, you can use the same. You don't need to convert the data into some other format for training. You can query directly the IDs and the embeddings of the ID or the representation of the pre-computed latents that you need in order to train. So all in the same place. So you always point to the same location. You don't need to pass around data sets and copy data to other people or other person, other department. You only have one pointer where the table lives. And now I will give way to Jack to talk about Lance.
Yeah, and this is probably the other side of the angle about how we worked with Netflix to get all these things. And from the perspective of a startup that is trying to build a format, Netflix has been super helpful. Among with all these companies, that we have a pretty vibrant community with a big group of different enterprises, frontier labs, and infrastructure companies that are supporting the whole format development. And our goal has been pretty straightforward. There has been an explosion of data since the LLM has taken off. I think we have been saying that the TB is the new TB and EB is the new PB, because it used to be that the company comes to us and say, I have a 3 terabyte of data, 3 petabyte of data, and we're like, wow, you are the top customer we have. And now it is like, okay, you are like 1,000 places down the line. And everyone is having a huge amount of data with videos, images, and documents all over the place. And then it caused all sorts of problems because the old infrastructure is not designed to support that. And as what Pablo has been saying, we came to the realization that we need a lakehouse to remove the data silos, because you don't want different data warehouses, different engines that are operating the data in different silos. But once you move to a lakehouse, you still have exactly the same problem when you're doing the AI infrastructure, because you still have to load data to a vector database, do a vector search. You still have to load data into like OpenSearch, Elasticsearch in order to do a full text search. And our vision is basically you still only need a single storage layer, but you can do all sorts of things on top of that, including vector, full text, SQL queries, and AI trainings, all using the same piece of data. And that is what we call the multimodal lakehouse vision. And that is also why we say, more recently, we are seeing Lance as a lakehouse format, because when many people see Lance as a file format, but actually, if you do a LanceDB create table, and you actually get a table, not a file format. And what is interesting is that every time we ask a person who uses us, they're like, I'm 100% sure I'm working with a file. And then we were like, are you sure? And then we literally see people that click into the file and realize actually it is a folder. So actually this is what it really is that all the blue layers are kind of what Lance provides, which is the format and library side of things versus the compute side of things. That we have the file format that is allowing the random access and high performance, and we have the table format that is doing what Pablo was saying about stitching different files in two dimensions, so you can add columns and also add rows at the same time in different use cases. And then there is a catalog that allows you to store the table and reference that in either your enterprise setting or if you want a storage-only experience. And then there is another layer, which is the SDKs that are used to talk to different compute engines. Either it is SQL or full text, or different search engines, or different training tools, so that it can actually be used throughout the whole pipeline. And from the format perspective, I think, as I just briefly talked about, the focus of different layers is to do the right thing at the right layer, so that we kind of, because so far there are different file formats, different table formats, and different catalogs popping all over the place, as I just showed in the last graph. And the divide of responsibility isn't really super clear, and maybe sometimes one layer is not doing the right thing, it's trying to do the other things, and it's not really doing that well. What we are really trying to do here is to make sure that we maximize the performance at every single layer and try to put the right thing at the right layer. So for the file format side, what we do is it is a columnar format that is 100% error native. We optimize on the random access because that is what the training is really needed for doing search, for doing random sampling, all those kind of AI-related operations. And we get rid of row group so that it is no longer bonded to that. And because the reason we can get rid of row group is that the table format is essentially our row group that you horizontally can grow in the object storage space without really being binded into have to have different groups within a single file. So that is what the two-dimensional storage offers. And on top of that, we create secondary indexes like the vector, full text search, scalar, geospatial, Bloom filter, all those different indexes, so that that is what is powering the full text search, the vector search natively on top of the storage. We also have other features like blob structure merge for faster upsert, and the large blobs I will talk a bit about afterwards as well. And on top of that, this is a part that really thanks to Netflix that has helped us shape this quite a bit, is the catalog layer. So today we offer two different catalog specs. One is what we call directory catalog. That is essentially, you have a list of tables in a directory. But it's more complicated than that because it offers transactional support and also all sorts of high performance operations so that you can really just have a catalog on storage. And then there's a REST catalog part that we worked with Netflix to essentially deliver an enterprise integration endpoint so that if you are using Lance, you can customize the endpoint. You can offer the same REST endpoint, and everything will plug through the whole ecosystem so that you can work with different engines, connecting to your internal custom catalog, and then the catalog stores Lance data. And on top of that is a layer I think not every similar solution has, which is what we call the namespace client spec. That is used really to standardize the interaction between the compute engine and the catalog layer so that we have the exactly same way when we connect to not just the direct catalog, the REST catalog, but also if you want to store Lance table in, like let's say Unity, Polaris, Gravity, and all these new catalogs, you can still do that, and it all works in exactly the same way. And on the other side, you will be able to connect to different compute engines. Another big reason we did this is because we want it to work in all different languages. I guess TypeScript is a big part of that because that is what all the agents are interacting with these days. And we have gained tremendous popularity, I think, since the past few years. That I think at this point we are the fastest growing format across all the other ones. And lots of that is thanks to lots of the AI waves. For example, LanceDB is a default memory plugin for OpenCloud. So if you have used OpenCloud, you probably are implicitly using LanceDB. So that made us really shooting through the sky at this point. And one of the most important feature, I think, for Lance is what Pablo has described multiple times, the data evolution feature. So I'm not really going into more details about that. But just the syntax here is you define a DEOF, and you can add column to that, and the backfill automatically happens. This is the single node version if you use the Lance Python SDK. There's also the Ray version I will show afterwards. Another most important feature is probably the blob support. We recently published a blog about that for the blob v2 that goes into this in much more depth. So if you're interested, please read the blog. But in short, what we do is that we store the blobs as a part of the Lance files. so that you don't have to store a URI and then jump to a URI to load it. And this is super critical when you are doing GPU training and you don't want the GPU to idle and just fetching data. So instead, you are just fetching the Lance files into the directly and reading the blobs in continuous chunks and then feeding to the GPU for training. And this is a Python example about how you are going to do that. There is an API, what we call take blobs, so that you can take the blobs from a continuous range and then do the read. When we say blob V2, the V2 essentially kind of bridge the gap because this works really well for training, which is, I think for video, roughly 5 megabytes, and for image, roughly, I don't know, 1 megabyte maximum. But if you do even more than that per image or per video, then it is still going to blow up the storage of a single file, which is people don't like. So what we do is in V2 is we offer different modes. The mode I was talking about is what we call the inline mode. And then there's a packed mode, which is we pack multiple images or videos in the same file and store it as a separate file. Or there is the dedicated mode, which is we store the image and video in a separate file itself, but they are adjacent next to each other, so they are still optimized for retrieval. And then there's external mode, which is you already have the images, videos, you just want to link to that. So all the four modes work together at the same time, while the user is only exposed to the simple API of just, I want to take the blobs, that's it. Or I want to load up a bunch of blobs. So that is the blob support that is operating and powering the training we described behind the scene. And for the reintegration, it is what I think, thanks a lot to Pablo's contributions to shape the whole shape of this. Today, with the community's help, we have a dedicated repo called LanceRay that is hosting all the Ray integration with Lance. It is essentially an extension of the Ray data API, but it does much more than Ray data. So you can still read Lance and write Lance and add columns as described. It also supports distributed indexing, distributed compaction, and GPU training, all sorts of things, all packaged in that single repo. So for people who are interested, please take a look at that. And if you're interested in contributing, that would be even better. Yeah, so that is how we integrate with each other. And that's the end of the talk.